Let us go on to the second video on the frequency domain representation of linear time invariant systems given by the discrete time Fourier series and the discrete time Fourier transforms. Let us go on by considering the relation between the time properties of the signal and the respective Fourier representation. If we consider the time property, that is, if a signal is periodic and continuous, it has been seen that the signal could be represented by a Fourier series which is of the continuous type. Similarly, if the signal is non-periodic and if it is continuous, it was observed that it could be represented by a Fourier transform. The next representation is how will a signal be represented if it is periodic in the discrete domain, similarly if it is non-periodic in the discrete domain. The solution is discrete time Fourier series for periodic discrete signals and discrete time Fourier transform for non-periodic discrete type of signals. Let us go on to see what each of these two types of signals are. When we consider about the discrete time Fourier series, x of k or x of n provide the complex description of the signal. The DTFS coefficients x of k are basically the frequency domain representation for x of n, which is generally represented in the time domain as we are all aware of, and each coefficient is associated with a complex sinusoid of different frequency representing k could be equal to 2, 3, 4, etc. Thus, the variable k determines the frequency of the sinusoid associated with x of k, so that x of k finally becomes a function of frequency. Basically, DTFS is the only Fourier representation which can be numerically evaluated and manipulated on a computer. Both x of n and x of k are characterized by finite set of numbers, thereby there is no integration which enables us to represent the DTFS on a computer. As a result, it is extensively used in numerical signal analysis and in system implementation, and the other three Fourier representations could be approximately represented using the DTFS. Let us now consider the equations of the discrete time Fourier series. Discrete time Fourier series is usually extended to periodic signals, and it is having usually a fundamental frequency of omega naught is going to be equal to 2 pi by n, and a fundamental period which is given by n, which tells us the number of values which are going to be considered for the evaluation. Thus, x of n is going to be equal to k equal to 0 to n minus 1 x of k e power j k omega naught n. This is the basic discrete Fourier series. Thus, from the n values of x of k, we can determine x of n. And for x of k, the expression is x of k is 1 by n, k equal to 0 to n minus 1 x of n e power minus j k omega naught n. Thus, from n values of x of n, x of k can be easily determined. Hence, it is obvious that given x of n and x of k, each other can be found out using the above two expressions with a fundamental frequency of omega naught. Let us go on to two simple problems in order to evaluate the coefficients of both x of n and x of k using the expressions of DTFS. Going on for the first problem, using suitable DTFS equation representation, the question states, evaluate the DTFS coefficients. What would be the expression? X of n is going to be equal to cos 6 pi by 17n plus pi by 3. It is obvious that n is equal to 17 from this particular expression, as can be seen here, and the expression that we would like to use for this would be the expression given by x of n is going to be equal to k equal to 0 to n minus 1 x of k e power j k omega naught n. Let us try to expand the cos expression using the general trigonometric expression cos theta is equal to 1 by 2 e power j theta plus e power minus j theta. Thereby, we get it as 1 by 2 e power j 6 pi by 17n plus pi by 3 plus e power minus j 6 pi by 17n plus pi by 3. Now, let us try to make the expression more specific to this particular form. Thereby, let us try to retain this particular form only, and since it's a plus sign, we could write this as e power j pi by 3. That is exactly what has been done. So, it is e power j pi by 3 into 2 pi by 17n, which is for 6 pi by 17n. Similarly, here it would be e power minus j pi by 3, that is for this particular value, and this would be retained as 3 into 2 pi by 17n. So, let us go on to inspect what would be the values of x of k at specific values of n. That is, x of k at k equal to 3 would be half into e power j pi by 3, as can be read from this particular expression, because e power j k omega naught n will have 3 into 2 pi by 17n, where k is 3 and this is 2 pi by 17. If we are to consider for k equal to minus 3, considering it as minus 3, this minus sign is considered inside, this coefficient also becomes 1 by 2 into e power j pi by 3. That's how we are getting the same value for k equal to minus 3 and for plus 3. Here the expression is considering instead of 0 to n minus 1 to minus n to plus n. And for all of the values of k from minus 8 to plus 8 other than plus 3 and minus 3, the value of the coefficient of x of k is found to be 0. Let us go on to one more problem of a similar type. Using the suitable DTFS equation representation, let us try to evaluate the DTFS coefficients. So, considering the problem, the first question is x of k is equal to cos 8 pi by 21 k. From here, it is obvious n is equal to 21 and omega naught is equal to 2 pi by n, which is 2 pi by 21. So, we are aware that it is a harmonic sinusoid of 4. Let us go on to see how the expression is needed to be evaluated. So, x of k is given by 1 by n, k equal to 0 to n minus 1, x of n e power minus jk omega naught n. So, thereby, on expanding the cos expression as before, we will be getting 1 by 2 e power minus j into minus 4 2 pi by 21k, that is for e power plus j theta, and e power minus j theta is retained as e power minus j 4 into 2 pi by 21k. So, on observing the expression, this is 1 by 2, this is an average because only two values exist, and x of n is 1 because this is a term which is required for k. It is a fourth integral multiple and omega naught is 2 pi by 21. Thereby, what we get is x of n is going to be equal to 1 for both plus 4 and for minus 4. And it is 0 for all other values extending from minus 10 to plus 10. Next, let us try to move on to discrete time Fourier transforms. This is generally applicable for non-periodic signals, and as usual, it is used to represent a discrete time signal as a superposition of complex sinusoids. The DTFT involves frequencies omega in the range of minus pi to plus pi and has the unit of radians. It is usually used to analyze the action of discrete time systems on discrete time signals. Let us go on to the two basic expressions of discrete time Fourier transforms. The first expression enables us to represent a signal in the discrete time domain into the frequency domain and is represented by x of ej omega is equal to n equal to minus infinity to plus infinity x of n e power j omega n. And if we have the frequency values, in order to get back the time domain values, the expression used is x of n is equal to 1 by 2 pi minus pi to plus pi x of ej omega into ej omega d omega. These two expressions are respectively called as the discrete time Fourier transform equation and the inverse discrete time Fourier transform equations. And they could be basically represented by using this expression x of n is going to be equal to x of ej omega, thereby giving us the two representations in this particular form. Let us go on to problems on discrete time Fourier transforms. The first problem is determine x of ej omega for the time domain signal given by x of n is equal to 3 by 4 power n u into n minus 4. Recalling the expression of x of ej omega, it is given by x of ej omega is equal to summation n equal to minus infinity to plus infinity x of n e power minus j omega n. Thus, our expression is going to be equivalent to m is equal to 4 to infinity 3 by 4 power n e power minus j omega n. M is equal to 4 is equivalent to the unit step starting from 4, and it does not have any negative values between minus 1 to infinity. Hence, we have changed the summation to be between 4 and infinity. Thereby, our expression becomes 3 by 4 into e power minus j omega the whole power n summation m equal to 4 to infinity. This is similar to the geometric progression expression given by k equal to 0 to n minus 1 ak 1 minus a power n divided by 1 minus a. We have seen a similar problem for discrete time convolution where we have written if the way summation changes by another value other than 0, we have also written this as that value power. The same thing could be extended here, thereby we would be getting it as 1 minus 3 by 4 e power j omega power 4 as the summation starts from 4, 1 minus 3 by 4 e power minus j omega. Next, let us go on for one more problem to determine the time domain signal given the frequency domain signal as x of ej omega is equal to cos 2 omega plus j sin 2 omega. Recalling the expression for determining the time domain signal in the case of DTFT, we recall that x of n is equal to 1 by 2 pi integration minus pi to plus pi x of e power j omega n d omega. Thus, the expression becomes 1 by 2 pi integration minus pi to plus pi e power j omega into 2 plus n d omega by the expression for orthogonality. Thus, our resultant is going to be, since we have it as e power j omega n plus 2 over the integration, we know that it is going to be an impulse function with the same shift, thereby it is delta n plus 2. Now, let us go on to consider finally the references. The first reference is Oppenheim and the second reference is Simon Haken, from which the concept of this particular video has been considered.